right ahead.
Yes. So just a second to move that. Okay. So thanks, Peter, and thanks for the organizers, David and Christian, for giving me the opportunity to talk here. And and thanks to Uli Schorbeck for giving this very clear introduction to DMRG. So I was right to not elaborate much more on it in my talk. And but I would rather like to focus on say the chemical applications of DMRG and what various types of it. And to begin with, so as a chemist, I'm usually interested in, say, predicting and well, looking at the chemistry of molecules that are essentially can have any element of the periodic table. And as you can see in this well, pictorial periodic table, each element in our table has a different use in our daily life, and that already reflects that we can expect different chemistry and different chemical behavior of these elements. And to motivate why it can be interesting to look not only at the upper part of the periodic table, but also at the lower part of the periodic table, I would like to introduce you a little bit to the liquid state of mercury. So that is a puzzle essentially that has been solved only recently by the group of Peter Schwertfeger in New Zealand and his co-workers. And so mercury is actually the only elemental metal liquid at room temperature. So there, so around room temperature, so 25 degrees or 298 Kelvin, mercury is liquid, whereas the only other metal that come close to a liquid state at room temperature or slightly above room temperature, that is actually cesium and gallium. And the chemical symbol Hg actually comes from hydroguron, which means liquid silver. And so the question is, why is mercury actually liquid at room temperature? And the answer, so if you look up chemistry textbooks, and here I apologize, so that it's a German chemistry textbook, so which is sort of a standard inorganic chemistry Bible in Germany. And that's the Holman Wieberg. And if you look at the 2016 edition, you essentially find some hand-waving arguments. I'm not going to read it here, but I'm just telling you, okay, there are some hand-waving arguments, which students, as a student, you just have to accept. And also Pekka Pikku, who is one of the pioneers, I mean, if not, I mean, one of the major pioneers in the field of relativistic quantum chemistry, he gives in some of his review articles also, again, just hand-waving arguments why mercury is liquid. And so this is not really acceptable. And so that is why I would say Peter Schwertfeger got intrigued by this and set out on a journey. And basically after 25 years of intense research in 2017, only then he was able to nail it down. And so the liquid state of mercury is essentially a relativistic effect. So that means, and to just a small extent, it's an electron correlation effect. If you look at the melting point, of mercury and across the group 12, then you can see that zinc and cadmium, they're melting much higher in temperature. And if you look at this as a function of, say, relativity, and I come to what relativity, what we mean by that, as a function of that, then if you look at this from a non-relativistic point of view, then mercury would actually be solid at room temperature. But if you include relativistic effects, then there's a huge gain, and it melts about 160 Kelvin lower in temperature. And that means it melts way below room temperature. And so, oops, sorry. So in a sense, when we want to look at the electronic structure of atoms and molecules composed of, say, elements from anywhere across the periodic table, then we have to consider not only, say, electron correlation and potentially the kind of finite-sized basis set that we want to represent our atoms in, but we also have to take into account what kind of Hamiltonian do we actually consider. So we have to think about, do we want to do non-relativistic calculations or maybe relativistic calculations, and when can we neglect what? And so the challenges for theory, so for quantum chemistry, to be able to predict the electronic structure faithfully for elements and molecules composed of elements across the periodic table, is actually in an accurate treatment of the electron correlation. So we should be able to include many different electronic configurations, in particular if you have partially filled near degenerate electronic shells. And that means preferably you would like to have multiconfigurational methods, maybe large active orbital spaces, and preferably you want to be able to do molecular orbital optimization. So meaning orbital optimization beyond a mean field picture. So including correlation in our orbital optimization procedure. And as Uli was talking about, one way that quantum chemistry is attacking this problem is the so-called complete active space self-consistent field approach, where you essentially divide your molecular orbital space into three different sets. One is the so-called inactive orbital space, where you assume that in every electronic configuration that is of some importance, each of these orbitals will always be doubly occupied. You have a secondary orbital space where you assume that in all configurations that are going to be important, none of the orbitals will actually be occupied. And then there's an active orbital space where you assume that each orbital can have any kind of occupation. So essentially what you would like to do is you would like to solve the full CI problem within that space and at the same time optimize the composition of the molecular orbitals for that space by taking into account also orbital rotations from the inactive space to the active one and from the active to the secondary space. And well, the problem is that traditional CI-based methods, so configuration interaction-based methods, they sort of hit an exponential scaling wall at around 18 electrons in 18 orbitals, something like that. So due to algorithmic advances in the past, this is now maybe going up to 20 and 20 or maybe 22 and 22, but that's sort of where traditional methods stop. So that means we need to resort to some efficient wave function parameterization. And just to mention a few here, so that could be some type of selected CI, that could be full CI quantum Monte Carlo or diffusion Monte Carlo. That could be variation 2 RDM methods, as we have, for example, also this afternoon. And of course, DMRG could also be one potential active space solver here. And I think I don't need to summarize too much here about the properties of DMRG. It's variational, it's size consistent, and it is an approximate full CI for a given active orbital space, approximate only because we have to choose a finite bond dimension. And in my case, the bond dimension, I call it M here. It was the capital D, I think, before in Uli's talk. And one issue that one has to be aware of is that only for large bond dimensions, the MPS wave function actually becomes invariant with respect to orbital rotations. So in principle, unlike a full CI wave function where active orbital rotations are redundant, they're actually non-redundant in a DMRG. And we have implemented this MPS MPO type of approach that Uli was sketching in his previous talk. We have implemented this in our code that is called QC Marquez. And well, we have been developing in the past quite some machinery around this MPO MPS based approach in our code, so we can handle different kind of Hamiltonians. We have parallelized it in a shared memory parallelization, and right now we are finishing up this MPI-based parallelization. We have interfaces to various quantum chemical codes. Maybe you find your favorite one also among the ones here. And we have developed a lot of different approach is just based on this on the DMAG ansatz. That this includes also vibrational DMAG. It includes also time-dependent DMAG. And but here I would like to mainly focus on the relativistic chemistry aspect. So how to include relativistic effects in an MPS wave function ansatz. And so the remaining part of the talk, I would like to mainly focus on that here. And that means we would like to be able to include relativistic effects, and that could be preferably scalar relativistic effects and possibly also spin-orbit coupling. And for those of you who actually who are not that familiar with that, let me briefly explain what I mean by relativistic effects. So relativistic effects are just a hypothetical construct denoting the difference between a relativistic, so a Dirac quantum mechanical, and a non-relativistic or Schrödinger quantum mechanical description of matter, where the Dirac quantum mechanical description actually is consistent with the Einsteinian principle of relativity, and a Schrödinger quantum mechanics is sort of consistent with the Galilean principle of relativity. And we know that in practice that this one is the true principle of relativity, and this not. So that means our world is actually relativistic. So that's why relativistic effects are just a hypothetical construct. And commonly, we distinguish two kinds of relativistic effects. So those are the kinematic or scalar relativistic effects, essentially those that change the kinetic energy operator, and spin-orbit coupling effects. So essentially the coupling of spin and angular momentum. And in chemistry, there are even different distinctions, but they're not of that much relevance here. So when we want to talk about relativistic quantum chemistry, then we typically can distinguish two types of approaches. And one are the so-called one-step approaches, and the other one the two-step approaches. And what's the difference? In the one-step approach, we include spin-orbit coupling and scalar relativistic effects right from the start. So that means we base our approach on either the Dirac Hamiltonian in a 4-component form, or in a 2-component, so that is sort of a electrons-only form. Or we can use a two-step approach where we first solve our electron correlation problem in an Hamiltonian H0 here, where this, for example, could be just a scalar relativistic or a non-relativistic Hamiltonian. And then we include spin-orbit coupling as sort of a perturbation and calculate the expectation values of the spin-orbit coupling operator in the basis of the eigenfunctions of our unperturbed Hamiltonian. And then we sort of end up with this generalized eigenvalue problem here, which we then solve. And this would give us then the solutions in the spin-orbit coupled basis. And this so-called state interaction approach, I would like to show you a little bit what this is all about. So, for example, a typical use case would be that we calculate some Cas-type wave functions. So, for example, we optimize a set of electronic states which are, say, a singlet and a triplet manifold. And so that means typically if you do that, then the singlet and the triplet states, they will have molecular orbitals or a set of molecular orbitals which are actually non-orthogonal. So here I showed this for an example of that are 7 electrons in 10 orbitals. So that is was for a plutonium dioxide, and these are the singlet and the triplet here. And you can see the less white it is, the more we are away from an orthogonal overlap matrix. So that this essentially represents the overlap matrix here. And where does this come from? So the problem when we deal with non-orthogonal orbitals, so for this, it is actually instructive to look at the anti-commutation relations for creation and annihilation operators in non-orthogonal basis. So if we do that, then we see that the anti-commutator of 2 creation operators always vanishes, as in standard second quantization theory, but the anti-commutator of a creation and annihilation operator actually does not. So it actually carries a overlap matrix element. And that was where the problem of dealing with non-orthogonal orbitals actually comes into play. So in a general case for an orthogonal set of so in an orthonormal MO basis, this anti-commutator vanishes, so, or at least gives this Dirac delta. But in the non-orthogonal case, it depends on this overlap matrix element, S here. And as a consequence, if we apply an annihilation operator on any kind of occupation number vector, so any sequence of creation operators acting on the vacuum, it just gives us not back a single occupation number vector as in the regular case, so as in an orthonormal basis, but it gives us a sum of occupation number vectors. So that means it actually is not so easy to efficiently compute transition matrix elements between non-orthogonal wave functions. Question is, can we do something about this? And the answer is yes. So we can actually define a new orbital basis through a transformation given as here, where the new basis phi bar is referred as the dual of the non-orthogonal basis phi. And they are said to form a bi-orthonormal system because now this overlap equation here holds. And the question is, how can we exploit that? So we introduce a bi-orthonormal creation annihilation operators in this way. And if we now look at the anti-commutator for a bi-orthonormal creation operator with an annihilation operator in a non-orthogonal basis, we can see, okay, now this gives us the standard anti-commutational relation back. And so if we want to transform one orbital basis to a bi-orthonormal basis and keep the other one in the non-orthogonal basis, then we also need to sort of counter-rotate the corresponding wave function. So if you rotate the molecular orbital basis, we need to counter-rotate the wave function as well. And it was actually shown by Per Malmquist how to do that efficiently. And we have implemented and formulated that for an MPS type of wave function, whereas Per Malmquist did that for CI type-based wave functions. And so the flow chart for this kind of approach would be, we loop over spin-free or scale-relativistic MPS wave functions. We check whether the MO bases of the various states are orthogonal to each other. If they're not, we transform one of them to the bi-orthonormal basis. And then once we're in this bi-orthonormal basis, then we counter-rotate the MPS wave function, and now we can compute the overlap matrix and the transition density matrix efficiently in that basis. And that also allows us then to compute spin-orbit coupling matrix elements in that basis. And once we have done that, we have the spin-free Hamiltonian plus the spin-orbit coupling matrix elements, and we can construct the spin-orbit coupled basis in that representation. And just to show you that it actually works, so we did that by comparing our D-G ansatz, where we optimize the molecular orbitals together with the D-G, solving the D-G problem. And here we took 20 triplet and 20 singlet states and compared it to a Cassis-Serf calculation. And essentially what you can see here is we more or less exactly reproduce the Cassis-Serf numbers. So that is a very nice feature of our approach. So we are able to more or less exactly reproduce the Cassis-Serf numbers here for the ground state of this plutonium dioxide, and also for excited states. And now, what about the one-step relativistic approaches? So this I've been working on with Ersch and Markus Reyer in Zurich, while Ersch was visiting us in Zurich back in 2014. And later on, we implemented that and made a new formulation also in our QC Marcus MPS code. And the idea behind that is we want to have a general formulation that works with any 4 or 2 component Hamiltonian, where the 1 electron operator is the Dirac operator as shown here, and the 2 electron operator could be any 2 electron operator. So that could be, for example, the Coulomb operator. It could be the Gaunt Albright operator itself. And the problem, or say the ansatz that we are choosing is a so-called Cramer's unrestricted spino model. So that means our local basis just consists of basically is the spinor occupied or empty, essentially. And if you want to use an efficient 2-component Hamiltonian, then there's one drawback with existing 2-component Hamiltonians. So formally, if I may go back just a bit, formally you can see that the 1 electron Dirac Hamiltonian contains this alpha and beta matrices here that I have shown here. So they're essentially the alpha matrix you can write as 2x2 matrices, where you have on the diagonal you have a 0 2x2 matrix, and on the off diagonal you have the polyspin matrix, and the beta matrix or the beta is given as here. And so that means you have sort of a 4-component you have a 4-component Hamiltonian, and therefore also your wave function has 4 components. But in quantum chemistry, we are essentially interested only in the electronic solutions, which are sort of described by the upper part of the 2 components, and the lower part of the 4 component, the other 2 components, they're actually sort of describing some kind of positronic solutions, which are not of very much interest in quantum chemistry. So therefore, we can also formulate a 2-component Hamiltonian, and there has been tremendous research in the past about this. And sort of the dominant these days is the so-called exact 2-component Hamiltonian, where this unitary transformation matrix can be computed exact in a given finite 1-particle basis set. And that allows you to exactly decouple your 1-electron Dirac Hamiltonian in the following way, so that you get a diagonal representation here. And then for quantum chemistry, you just keep that one here. But the problem comes with the 2-electron part. So if you want to do the same decoupling for the 2-electron part, you would end up with this kind of equation here. And you just need to keep that one here. So that would give you the 2-component Hamiltonian. But the problem is, as you can see here, this transformation would actually require the knowledge of the full 2-electron integrals in a 4-component basis. So essentially, it's sort of an n to the 5 problem that you would try to solve. So the problem becomes even more complex than it actually needs to be. So a common approximation is to not calculate this object here, but actually take the 2-electron part of your operator as just the upper untransformed block here. And the difference with respect to the true block here, that is known as the picture change error. And what we have done in recent months is actually to devise a scheme that sort of remedies these picture change errors here to a maximum possible. So essentially to bring this difference to essentially 0. And we term this so-called exact amphi or X-amphi, where we provide atomic mean field 2-electron scalar relativistic and spin-orbit corrections to be used with this X to C Hamiltonian. And it replaces any kind of atomic mean field approach that was previously based on first-order mean field spin-orbit corrections. And the nice thing is, as I will show in a minute, is it yields picture change corrections for the core and the valence space, whereas in previous times, there were only corrections essentially available for the valence space. It works for any 1-particle basis set, and these corrections can actually be pre-computed and made available as a library. So, and I said recently, so actually I just finished the implementation yesterday, so this is really just very recent data. And so the first thing we look at here is so-called the SCF or Hartree-Fock overall energies for organesson. So organesson is element 118, so it's the last known element in a periodic table. And we look at this with the dial double theta base set, just to begin with. And so what you see here, so these are the orbital or spinor energies for the Dirac-Coulomb Hamiltonian. So this is the sort of the exact result. And what you see here is with our X to C X amphi scheme, we exactly reproduce the 4-component data. Yeah, okay, thank you. Whereas with this X to C A here, which is the old sort of first order spin orbit correction code, you can see that in particular in the core region, there are huge differences. So these are Hartree values. So there are huge differences here. And if you don't do any picture change corrections at all, you essentially get almost the same here because these are not designed for correcting in the core. So if we go to the valence, so let's jump down here. So again, with our X amphi scheme, we reproduce the 4-component numbers, and also the old scheme works essentially pretty well. And you can see if you neglect spin orbit picture change corrections in the valence, this is not a good idea. So the bare X to C Hamiltonian is essentially not recommended to use. So as I said, it works particularly well for core properties. And therefore, we looked also at core ionization energies. So this is now the acetate ion. We're looking at the at various edges of the ionization of the acetate ion. And this we did with the equation of motion couple cluster in a triple theta base set. And now the data is all in EV. And you can see this is sort of the reference number here. For the K edge, so ionizing the 1s, you essentially get 3,538 electron volts, and we reproduce that with our X amphi scheme very well. Whereas with the old one, or without any picture change corrections, you're off by at least 6 electron volt. So you're quite off. So it becomes a little bit better if you go to the higher edges, so the L1, L2, and L3 edge. And coming in also to the zero field splitting of some pi star 2 systems, so essentially the higher homologs of the oxygen dimer. Here we looked at again at say the various states you have in the so the various electronic states you have in the valence space, and here actually our new scheme and the old one compared to the Dirac-Coulomb reference works actually pretty well. And so that is a nice thing. So we are actually able to reproduce the 4-component numbers pretty well. And that brings me to some more examples for uranium complexes. So here we, for example, looked at the ground and excited states of some prototypical F1 and F2 complexes. So we did a state average DMRG SCF optimization, including 14 routes for an F1 system, so the uranium hexachloride anion. And for the dianion, which is an F2 system, we included slightly more states in our state averaging procedure. And we looked at the excitation energies and compared it to experimental numbers. And you can see with our CAS 19 and 32 DMRG ansatz, we're actually reproducing the experimental numbers pretty well, and doing also pretty well compared to, say, literature values, which are sort of standard in ab initio quantum chemistry. And the same also holds for the dianion. So here, again, our CAS 20 electrons and 32 spinors works pretty well for the low-lying, for the ground state, and also for the low-lying excited states, in particular compared to experiment. So that's very nice. And why is that so? So why can you essentially approximate the low-lying valence spectrum of these molecules with just a small CAS ansatz, so 20 electrons and 32 orbitals? That's essentially because the low-lying states are more or less just dominated by FF type of excitations. So as long as you include the F orbitals and F electrons in your active space, you're pretty much set and done. So we correlated also the 6p spinors and also the valence chlorine 3p spinors. But as you can see here, the occupation numbers are essentially just 1. So in all of the states, so they're more or less inactive, if you like. And finally, I want to show a little bit. So if I have 1 more minute. So finally, one last thing that we just looked at is the coupling to strong external magnetic fields. And the idea here is that atoms and molecules may exhibit actually exotic chemistry in strong magnetic fields, where there has been a particular example shown by Trygve Helgake and co-workers a couple of years ago, where a new type of molecular bonding actually shows up for the hydrogen molecule in a strong magnetic field. So essentially what you need to do is you need to place your momentum operator by adding a vector potential in your quantum mechanical ansatz, and you need to make sure that your atomic overall basis becomes gauge independent. And you need to remember that the interaction with an external magnetic field actually breaks the time reversal symmetry in a relativistic framework. So we looked at the bismuth benzene, which is sort of the heavy analog of pyridine, where you have instead of the nitrogen a bismuth here. And we looked at the orbital entropies as a function of the magnetic field strength. And what we can find is if we have no magnetic field, then essentially we find that the pi orbitals within that ring are more or less correlated. But as soon as we crank up the magnetic field up to 600 Tesla, there's something going on. And we're currently analyzing sort of how the entanglement changes if you crank up the magnetic field. I mean, what kind of chemistry does that imply? And with this, I would like to conclude. So we have been working on efficient relativistic correlation methods in the past, which allow us to look at various electronic and magnetic properties. And in the future, we would like to also do real-time time-dependent approaches to look at excited state chemistry more closely, in particular of heavy elements. And we also need to include dynamical correlation in our picture. And this we want to do in a sort of hybrid type of approach by coupling wave function theory to density functional theory. With this, I would like to thank you for your kind attention and thank my collaborators.
Thank you very much indeed. Do we have any questions? Maybe I can start. If you have some uranium-5 complex or whatever, there are quite a few electronically excited states. Do you have to worry about temperature, or do all those states have the same properties? I don't know, it depends on what chemical question you want to ask. I mean, do you have to, what do you do about that?
Yeah, so I mean, in this case of say the low-lying excited state spectrum, there it's sufficient to just, in this case you can simply consider them all, and as you can as you saw here, there are actually a number of say for example in this uranium-4 complex here. You have a number of degenerate states. So if we want to model the experimental spectrum, so here not much is known about say the vibrational regression, unfortunately. So only for the higher lying excited states, but that we haven't looked at. But clearly, I mean, if you want to sort of model the experimental spectrum apart from, say, just a stick spectrum, then we would need to include also finite temperature effects. Yes, that's for sure.
Thank you. Honor, please go ahead.
Thank you very much. This nice talk. I have a question regarding nonorthogonal orbitals. Is there any physical interpretation of the amplitudes in a quantum state written in the basis of B orthonormal orbitals? And one more question, do we know how to take partial trace in this basis?
Yeah, so essentially the transformation to bi-orthonormal basis. So what you're asking is, can we, for example, would that change the single orbital and single orbital entropies, and for example also the two orbital entropies? Yeah. So I haven't looked at this for this particular example, but you would expect that it actually changes, yes. But you can since you, after the transformation to bi-orthonormal basis, you have an exact representation of your MPS, so you can actually take the traces again. So you can compute the 1 and 2 orbital reduced density matrix in that basis. So
I think the same bases are also used in the research theory of quantum superposition. In quantum information, they call this basis as complement basis, as far as I know.
Okay.
And I think there can be some operational interpretation of these wave functions written in the bi-orthonormal basis. This is why I am asking this question.
Okay. I did not know that. That's okay. I have to look into that. Thank you.
Thanks a lot.
Do we have any more? Time for one more question, if anyone wants. Okay, it looks like not. So let's thank Stefan once again.
Thank you.
And the final talk of the